and welcome to the YouTube channel for Wayne State University's chapter of the Tau Beta Pi Engineering Honor Society. My name is Austin Heitzman, and I am back again with another linear algebra tutorial video, and today we will be looking at the inverse of square matrices. So to start, we need to look at what a square identity matrix is. We've mentioned square a couple times, but just as a reminder, this basically means that it is an n by n matrix. And what does that mean? The number of rows is equal to the number of columns. If I can squeeze that in there. Remember, row by column, they're the same number, so it's going to be equal. And so an identity matrix is going to be a square matrix. So it's going to be an n by n matrix with ones along diagonal and 0 everywhere else. And it can be generalized like this right here, where all the dots are just like as an etc. But if you need something a little bit more concrete, 2 by 2 would basically look like this. A 3 by 3, a little bigger, but the same idea. Four by 4. And so on. So you see they always got the ones down the diagonal like this. Everything else is 0 in every single case. And you can see like it kind of needs to be a square matrix for that to be the case, right? Because if we had like a 2 by 3, well, that would be 2 rows and 3 columns. Well, how can we have like a diagonal if it's not even, right? So that just doesn't work. Gotta be a square matrix. And the fun part about this is that this is necessarily commutative. So what I mean by that is that if you are going to multiply like some matrix A by I, that's going to be the same thing as the identity matrix times A, because it's just ones, right? And you know, that is pretty much the idea, right? I mean, this is a generalization of the number 1, because just like in multiplication, some number C times 1 is always going to be that number, right? Well, in matrix form, some matrix A times identity is always going to be A. Now, you may be wondering why the heck this matters. Well, it's going to come in a lot of handy when we start looking at inverse matrices. So to define this, we're going to let A be some n by n matrix. If there is a B such that A times B is equal to the identity matrix, which inherently would be equal to B times A, then B is the inverse of A. And in this case, we would write it, what we're calling B up here, we're usually going to write as A with a -1 superscript. Now note, please note, that this is not an exponent. We are not going to be taking any matrix to the power of -1/2, or -1 I should say. If we remember from the last video, we do not divide by matrices, so that would not make any sense. This is just a notation, how we use this. So, now that we have our definitions under the belt, let's look at how to calculate this. We're going to start by 2x2 matrices, because this has a handy little formula. So if you have a 2x2 matrix A that looks like this general A, B, C, D, then if the inverse exists, A1 would look like 1 over, we're going to do AD minus BC times a different matrix that's pretty similar. We're going to do D, -B, -C, A. Right? So these guys have swapped, and these guys are exactly where they were, they just changed signs. Right? So this might not look like it makes a lot of sense right now, but basically an inverse matrix is still a matrix, right? So the idea is that you're just going to take this quotient as a scalar multiple of this matrix, right? And later on, we're going to see that this right here is pretty important. But right now, let's just take it as a formula. And this is a really, really handy formula to memorize, because you can do a calculation like this kind of the long way, which we'll get into it in a second, but it is so much easier to do it straight from the formula. Now, note that this formula only works for a 2x2 matrix. So what do we do in the other case? Well, it's basically going to be a little bit of a process. So the way that I break this up is just in a few simple steps, though the steps themselves can get a little convoluted, you could say. The first step is going to be to augment, right? And what that means is, say we have a matrix A, and for writing's sake, I'm going to use a 2x2 matrix, but the idea is to have bigger ones at this point. So this is a 2x2 matrix, and remember we talked about an identity matrix, which can be any size square, right? So we are going to augment A. If you remember augmented matrices, we're just going to draw this line. Going to augment it with the identity matrix of the same size of A. Okay? Now, from here, we want to reduce it. We want to put it into reduced row echelon form, right? And I'm not going to do that whole process for this general example because we're going to get a lot of messy letters, but basically what that's going to look like after you do all of your nice steps, and don't make any mistakes, hopefully. Basically the side that we did have A on is now going to be the identity side, and the side that was the identity is going to be the inverse matrix. And knowing that, that is pretty much what we need to interpret, right? So by the time you get it down into reduced row echelon form and you're looking at the left side as what is now an identity matrix, right? Because reduced row echelon form is essentially just an identity matrix. The right hand side, which used to have the identity matrix, will now have your inverse of A. So this is pretty handy, right? I mean, from there, this might clear things up from what we talked about with the 2x2, having this matrix on the side here. It is going to be a matrix, right? So before we get into some examples, there's just a couple small little properties. Thankfully, there's not like a billion of them like they were for matrix algebra. For identity matrices, there's just a couple that we really need to remember. The first is that if you have A and B in parentheses and you want to invert that, it's not quite commutative, but it does equal B inverse times A inverse. So basically, like, these guys flip. And the only other property we need to remember is regarding that 2x2 formula. So I'm just going to rewrite the A inverse equals 1 over AD minus BC times the matrix D negative B negative C A. This exists only if that denominator, AD minus BC, does not equal 0. This is going to be really important in a couple sections from now, but for now, it's sufficient to just understand that. And that really makes a lot of sense when you're considering what we're doing here, right? Because this is going in the denominator, right? So if that's 0, this whole thing falls apart. It's undefined. So that's just going to be a handy thing to remember. And this is definitely a formula, if I haven't mentioned this already, that you want to memorize. Just going to be so much easier. And the way you memorize that is by writing it out a billion times. So I encourage you to do so. All right, so we're going to look at a couple examples here. And I have a couple just to show some different cases, but it's not going to take terribly long. So the first one is going to be a 2x2 matrix, so we can kind of see how that first formula is working, right? So first, for a 2x2 matrix, since we just established that AD minus BC must not be 0 in order for inverse A to exist, before we even try to write the formula, let's see if it even exists, right? So AD minus BC, in this case, is going to equal 2 times 5 minus 7 times 1, right? AD minus BC. And this is clearly not 0, but we're going to need it anyway, so I'm just going to calculate it as 3, right? So now we can take this and plug it into our formula. Again, we're writing it out a billion times so that we remember it. The inverse of A is 1 over AD minus BC times the matrix D negative B negative C A. And when we plug our numbers into this, we're going to get 1 over what we just calculated, which is 3. And then the matrix, we're going to swap A and D. So the diagonal is going to be 5, 2. And then we're just going to take the opposite of B and C. So it would be negative 7, negative 1. And the idea is basically that if you wanted to distribute that in, it would just be like 5/3, negative 7/3, negative 1/3, and 2/3, right? But this is really the way that we like to keep it. It keeps it nice and clean. It's very easy to tell what's going on. I just wanted to show you just so you kind of understand like why we have a number out in front. Okay, we're going to start looking at some 2x2 matrices. And for this guy, I wanted to give kind of an example because I mentioned that inverses do not always exist, right? And we just saw that in terms of 2x2, right? Where AD minus BC must not equal 0 if A inverse exists. So for a 3x3 matrix, it's not quite as simple as taking the diagonal, right? Because you know it's only really available for 2x2 matrix for now. However, in this form, we can fairly clearly say, like, if we want to bring this down to reduced row echelon form, right, because that's going to be our main step, there's really not a way to do that, right? I mean, this guy is a 3, so, I mean, even if we divided everything by 3 and got that down to 1, what are we going to do now, right? Because as soon as we do this step, if you remember, for row reductions, we can add row 2 to row 3 and get row 3. Well, that is just going to give a row of zeros. And once we've appended the identity matrix to that, it will be obvious that this is inconsistent, right? This does not reduce to reduced row echelon form, so there is no inverse. That's all you gotta do. So, for the last example, let's actually look at a real one, shall we? So I'm going to be working a little bit quickly through the row reduction because we've already done it a few times. However, I have learned by brutal experience that it is very easy to mess this up. So when you're practicing, go slowly, don't skip steps, and it can be quite a pain in the neck trying to trace down an error. So just word of caution. Okay, so if we're looking to find A inverse from this given A, well, our first step is to append, right? So I'm going to copy down this matrix that was given as the left-hand side of what we're working with. And I'm going to draw this line, and I am going to write a 3 by 3 identity matrix. All right, now you might be wondering up until now, like, why this will even change. Well, when we do the row reduction, we need to carry it all the way through both sides of this, right? So my first move for getting this down to reduced row echelon form, I see that 0 cannot really be a good pivot, but 1 would be a great pivot. So let us make our first step to interchange rows 1 and 3. Well, and I'm also going to interchange the rows on that right side. All right, from here, probably see I can do -3 times R1 plus R2 to get the new R2. I can just copy down the first and third rows because that is not, in essence, changing. -3 times 2 is going to be -6 plus 1 is -5. And 3 plus 4, or 3 plus 1 is 4. So now I'm going to do the same thing on this side, right? So that's going to stay 0. We have 1 right here. And then I have a -3 plus 0 is going to be -3. You can already see that kind of starting to form, right? So from here, I see that 1 is a much better pivot than -5, right? So I'm going to flip these two rows again and do an interchange of rows 2 and 3. Kind of did a dumb thing writing this so far onto the side, but that's quite all right. 1. Now row 3 becomes row 2 and vice versa. Be very careful copying these things down. Yes. All right. from here I'm going to do 5 times row 2 plus row 3 is going to be my row 3. I'm going to do it kind of down here this time so that I can see it when I'm copying. All right, 0 here, that's going to be a 0, which is what we wanted. And -5 plus 4 is -1. It's going to make our next step pretty easy, huh? 5 and -3. All right. Working on down. The only thing that needs to change for this one is going to be to flip the sign, right? So I'm going to do negative row 3 is row 3. And bear with me as I copy this a billion times. I don't think I've ever had my hand hurt quite as much as I did on my last linear algebra exam. -5, -1, and +3, right? Okay, now we just need to do our back substitution to clear out these and make them all zeros, right? Steps 6 and 7 are going to be pretty easy. We're just going to take row 3 plus row 2 as row 2, and row 3 plus row 1 as row 1. And if all of this is making your head spin and getting you very lost, I highly suggest you check out the past videos where we really dove into row reduction. From here, I'm going to copy down row 3 first because that's not changing. All right, 1 minus 1 is going to be 0. I have a -5 plus 1. It's -4, -1 plus 0 is -1, and a 3 plus 0 is 3. And then row 1 is going to come out in pretty much the same way. One tiny last step, we just need to get rid of this 2 right here, yeah? So step 8, how can I do that? I can take -2 times row 2 and add it to row 1 to get my new row 1. And that will do us, right? It's going to be a 0 and 0. All right, -2 times 4 is 8, -5 will be 3. It's going to give us 2 minus 1 is 1, -6 plus 1 is -5. And I'm actually just seeing, like I mentioned, it's very easy to make mistakes. This part right here, I've added 3 to 1, so this cell should be a 4, not a 1. Which means this guy is in fact a -2. All right. Thankfully that was a small one, but everything else should be correct. And the nice part about this is that, again, it's very easy to check, right? So the idea, our claim here, after doing all this work, is that A1 exists, or A inverse exists, and we know that because this side is equal to the identity matrix, right? So then this side will be A inverse. So I'm just going to move this down a little bit. A inverse is just this matrix that we came up with after doing our row reduction. And if you'll remember, our initial claim, what we learned, so this is going to be our formula, right, to remember that. But the handy thing about this is that if you multiply the original A times A inverse, this whole thing means that you're going to get the identity matrix if you've done it right. Yeah, so it is a little bit tedious to check. However, on a test, on a quiz, it is well worth it. I'm just going to walk us through that really quick just so that you are like totally comfortable with what that looks like. Just gonna make sure. Yes, I have this written down in front of me, so I'm just going to copy it from there. So this right here is our original A. This is what we were working with. And I'm going to multiply it by our A inverse. Again, if you're not too familiar with how to multiply matrices, I refer you back to one of our previous videos. So I'm going to run through it really quick. We're going to have 0 times -4 plus 5, right? That's going to be 1. We're in good shape so far. 0 minus 1 plus 1 is 0. 0 plus 3 minus 3 is 0. We have 9 minus 4 minus 5, 0. 3 minus 1 minus 1 is 1. And -6 plus 6 is 0. Home stretch, we got 3 minus 8 plus 5 is not always obviously 0, but it is indeed 0. 1 minus 2 plus 1 is 0. And a -2 plus 6 minus 3 is 1. Right? And that does equal the identity matrix, so we know we have done our work correctly. It is very worth checking this, and it is also extremely worth actually going through and checking all of it, even if you're off to a good start. Sometimes an error is hidden right in that last cell. And through doing this a billion times, I'm not going to demonstrate this very clearly, but I encourage you to keep an eye on it when you're doing your practice. I have kind of noticed that when you try to form the identity matrix, if you start getting actual numbers besides 0 and 1, I want you to pay attention with like where those are, and then go back and fix the error and pay attention to where the error actually was in the inverse matrix. You're going to see that like the columns and the rows that you have the error kind of indicate where the error actually lies in the inverse matrix. So that's just a tip that I have learned after making so many mistakes on so many of these before finally getting comfortable with it. So that's a lesson for today. Just keep at it, and this will become second nature soon enough. If you need to refer to any previous lectures, you can find them on our channel, as well as any other videos that you may be looking for, be it in chemistry, other branches of math, or mechanics, pretty much any STEM-based lecture. We are working to expand greatly, so I encourage you to subscribe. I will be back soon with section 1.5, so stay tuned, and until then, I hope you have a great day.